Hey everyone, let's talk about something that is happening literally all around us and inside of us every single moment of every day. Chemical reactions. And it all boils down to a really simple question.
Really think about that. When you bake a cake, can you unbake it? When you light a match, can it go back to being an unlit match? Do these changes only ever move forward? Well, let's dive in and find out.
To make this super simple, let's just think about traffic. Some roads are one-way streets, right? Once you head down, that's it. There's no turning back. But other roads are two-way streets. You can go down and you can come right back. And believe it or not, chemical reactions work in a very, very similar way.
So first up, let's talk about that one-way street. In the world of chemistry, this is a reaction that is all about one thing, moving forward. This is what we call an irreversible reaction. Irreversible is a big word, but it's a simple idea. It just means all your starting ingredients, which scientists call reactants, get totally used up to make something new, which they call products. And once you've made those products, there's no going back. A perfect everyday example is just burning something, like a piece of charcoal. The carbon in the charcoal mixes with oxygen from the air and, poof, you get carbon dioxide gas. Now, the most important thing on this slide is that single little arrow pointing to the right. That arrow is like a big no U-turn sign. It's telling us this reaction only goes in one direction. You can't just grab that carbon dioxide out of the air and turn it back into a piece of charcoal. Okay, but what about those two-way streets? This is where chemistry gets really, really interesting. Some reactions are totally different. They love to play a constant back-and-forth game. This is a reversible reaction, and it's kind of wild. It's a process where the starting stuff is turning into new stuff, but at the exact same time, the new stuff is turning back into the starting stuff. It's all happening at once. Here's a classic example, making something called hydrogen iodide. Now, I want you to look really closely at the symbol in the middle of that equation. You see it? Those two half arrows pointing in opposite directions? That is the special symbol in chemistry for a two-way street. It tells us that while hydrogen and iodine are busy making hydrogen iodide, the hydrogen iodide is just as busy breaking back down into hydrogen and iodine. So these two-way reactions, they kind of play by their own set of rules. For one, you can start from either side. You can start with the ingredients, or you can start with the final product, and the reaction will still work. And because it's always going back and forth, it never really finishes. It's always trying to find a perfect balance point, a state that scientists call equilibrium. And of course, it always uses that special double arrow. Okay, so you're probably thinking, got it. One way and two way. Simple enough. Well, now I'm going to let you in on a little secret. A secret that kind of changes everything. That's right. In theory, there isn't really such a thing as a true one-way reaction. Every single chemical reaction can, if the conditions are just right, go backward. So why do we even call them one-way reactions? Well, it's because the backward journey is just incredibly, unbelievably slow. So slow that for you and me, it basically looks like it's not happening at all. So that leads to a pretty cool question, doesn't it? If all reactions are secretly two-way streets, can we, block off one of the lanes? Can we force a reaction to go only one way? And the answer is a big yes. Chemists have some really clever ways to put up a do not enter sign on that return trip. Let's check them out. There are basically three main tricks for making a two-way reaction act like a one-way street. And the whole idea behind all three is really simple. Just get rid of one of the products as soon as it's made. Because, hey, if a product isn't there anymore, it can't be part of the backward reaction. First up, just let a gas escape. So, let's say you heat up limestone. It breaks down, and one of the things it makes is carbon dioxide gas. If you're doing this in a jar with no lid, that gas just floats away, it's gone. And since it's not there anymore, the reaction can't go in reverse. It's forced to just keep moving forward. The second trick is pretty similar. Remove a solid. Sometimes when you mix two liquids together, a solid suddenly appears out of nowhere. It clumps together and sinks to the bottom. Scientists call this a precipitate. Well, because that solid has dropped out of the mix, it's out of the game. It can't be used for the reverse reaction. And just like that, you've created another one-way street. And this third way is super clever. You get rid of a product by making it react with something else. For instance, in this reaction here, one of the products is acetic acid. But if you add something else to the mix, like sodium hydroxide, it immediately attacks the acetic acid, gobbling it up and turning it into something new. No more acetic acid means, you guessed it, no more backward reaction. So, okay, we've got one-way streets, two-way streets, and a bunch of tricks to block off a lane. But why does any of this really matter? Well, it's because understanding this stuff is the key to controlling chemistry and making all the things we use every day.
So let's do a quick recap. We learned that reactions are like roads. Some are one-way, some are two-way. We learned that the arrow is like a road sign, telling you which way to go. We found out about the big secret, that pretty much all reactions are actually two-way. And finally, we saw how we can be the traffic cops and force a reaction to go forward by just removing one of the products.
And that brings us to one last thought. Being able to control reactions is awesome for making medicines or new materials. But sometimes, nature needs that two-way street to work. So I'll leave you with this question to think about. What reactions out there in the world, or even happening inside your own body right now, absolutely have to be two-way streets to work properly? Thanks for exploring this with me today.